Okay, so today we'll discuss the confidentiality. The confidentiality essentially means that to keep some content secret in the message channel. And here we can propose a simple model of that. So we have Alice who sends the message and Bob that receives it. And in the middle of the message channel, there's an eavesdropper who sees each text running through the channel. And here's how they keep message P confidential. So they will agree on a secret key K and a pair of encryption and decryption function, E and D, which are generated by the key. So Alice will encrypt the message before put it to the channel, and they hope that only the one with the secret key, which is Bob, can successfully decrypt the ciphertext. So the most important observation of the model here is that we believe that the confidentiality of the message totally comes from the secrecy of the secret key. And we didn't make any assumptions on the design of encryption and decryption functions themselves. So we need to be careful because it is possible that for some functions, the attacker can somehow exploit them and surpass the secret key to decrypt the message. And we will see several different encryption functions later. And for each function, the first question you want to ask is that whether you can decrypt it without knowing the secret key. So the first cipher here is called the Caesar cipher, which is pretty classic, and it works on character strings. So we can pick a secret number K as the offset, and then we can replace each character in the input string with the K character down the alphabet. And for example, we choose KS3 and the plain text as Fox, then the output should be IRA. And in this case, we can actually surpass the key because, first of all, if we know that a message is encrypted by the Caesar cipher, then because every alphabet is finite, the value of the secret key can exceed the capacity of alphabet. And we can just try every K and see if some choice leads to the readable text. And further, if we don't know that it is Caesar cipher, we can still use statistics to recognize that there is a great chance that it is. So if we take just one step further from Caesar cipher, we can get the Virginia cipher, which choose a secret number letter rather than one secret number. And it uses this secret letter to mask the original text block by block. But unfortunately, we still can use the statistical method called the Kosinski method to decrypt the cipher without knowing the secret string. So now let's see what the modern scheme for encryption do. And this scheme is called the one-time pad. And the idea is simple. We just generate a real random bit string and XOR the string with the message. So the advantage of this method is that because the string is truly random, the attacker can theoretically does not know better than guessing. So this method is like the Platonic perfect cipher to use. But unfortunately, this method is very impractical in reality for two reasons. So first is that because a truly random string is really hard to generate, especially for a very big input. And secondly, for sake of security, we must not reuse any pad. Otherwise, the XOR of two cipher may still explore some information of original text like the result here. So these two factors makes the one-time pad really efficient. But however, it is still good to know because now we can regard it as the theoretical upper bound of confidentiality we can obtain. And the next thing we need to do is to refine some parts of this method and see whether we can improve the efficiency without losing too much confidentiality. So one trial of the refinement is called the stream cipher. And the idea is that we don't use the truly random string to XOR with a message. Instead, we use a secret key and use it to generate a pseudo-random string for padding and for masking, sorry. And Because this K can be really small and we're actually using a pseudo-random generator rather than generating truly random string, the complexity of the algorithm can be much lower than the one-time pad. But also because we are using a pseudo-random algorithm, so the confidentiality actually counts on whether it is really pseudo-random. And another trial, and the more ubiquitous one, is called the block cipher. So the idea of block cipher is that we also choose a secret key K, and we can split the message into several fixed-sized blocks. And for each block, we can use this key K to generate a pseudo-random permutation and act it on each original block. So now, same as the stream cipher, since we used a pseudo-random algorithm, the confidentiality also counts on whether the algorithm is really pseudo-random. So there are a couple of questions or problems about the block cipher. So the first one is that in order to encrypt the arbitrary sized message, we need to somehow deal with the last block of message because it doesn't necessarily fit the size of the block. And naturally, we just pad this block to the required size. And we use the approach so-called the PKCS 7 standard, which means that the padding bytes are all the numerical value of the padding length. So for example, if we need to pad 3 bytes in the last block, then we just set each block of padding as 3. So in this case, we can see that the padding length is actually self-contained in the message. And so we can identify the padding portion once after the decryption. And another problem with the block cipher is that how can we apply the block cipher to a sequence of blocks? So as you can see that if we simply encrypt each block independently, it may still expose the information of the original message, even in the cipher. So we need to design an algorithm for it. And officially, we call these algorithms cipher modes. So here we have two types of cipher modes. The first one is called the cipher block chaining, or CBC mode. So its idea is that we can use the ciphertext of the former block to encrypt the latter block. Here, for example, for this portion, this plaintext is first XOR with the ciphertext of the former plaintext. And after that, the result of XOR will be sent to the block cipher. And specifically for the first plaintext, since it doesn't have any former block, we just define an initialization vector to XOR with it before sending it to the block cipher. So there's also another mode called the counter mode. The idea of counter mode is that we can actually convert a block cipher into a stream cipher. So specifically means we can use the block cipher to generate a pseudo-random string to max the whole plain text. And basically what we do is that we can choose a unique nonce, which is a string. And also for each plain text, we will first get which part is it in the original overall plain text. And we append the announce and the counter string together and send this to the block cipher to get the mask we want and XOR it with the plaintext to get the ciphertext.